And one cool thing about JavaScript is that it works like a glue on the internet. I mean, in addition of being the main programming language used on the client side of web applications, we have like frameworks like the Google Web Toolkit that compiles Java and Python code into JavaScript. So it's like an assembly, like putting the internet together. So I mean, running JavaScript efficiently is important, but it's a challenge because this language is very dynamic. So it's hard for the compiler to run it efficiently, to compile it efficiently. And we have also this thing with the browser war. So we have seen a lot of very good JavaScript technology, like compilation technology, coming in recent years. So we have Google's V8 resurrecting some ideas from Self, one of the seminal programming languages in the literature. So it tries to convert objects into vtables, into classes. We have Mozilla's Trace Monkey. It was a paper in PLGI in 2009 that talks about how to trace compilation for JavaScript. We have Jaeger Monkey now, which does type inference. There was a paper on PLGI last year about doing type inference for JavaScript. So we have some academic work on JavaScript. So what's the key observation? We have instrumented the Firefox browser, and we have used it to visit the 100 most visited pages according to the Alexa website. This methodology is not new. You're following the work of Richards et al. So we use jQuery to design some automatic scripts that try to imitate a user, like a user section on one of those web pages, and then we log everything that we get. So we also have used the same methodology to analyze some benchmarks. We took through three: SunSpider, V8, and Kraken, and that's what we got. This is for the web pages. So here I have a histogram. The bars are like the number of functions. I'm analyzing a corpus of 23,000 functions. So most of the functions in the web pages, they were called just once. Like 48.8% of the functions were called just once. And we have like a clear power distribution here. Most of the functions are called a few times, and we have a few functions which are called many times. And if I analyze how many times the function is called with the same parameters, the same arguments, distribution is even more impressive. I mean, you have like almost 60% of the functions always being called with the same arguments. This in the web pages, the 100 most visited web pages. And this number sort of translates into the benchmarks as well. But here I'm analyzing a corpus which is much smaller. I have like around 600 JavaScript functions. But we see that we have like a distribution towards the left side. So most of the functions, they are called a few times. And we have a few functions called many times. And this is more clear, like down here, I have functions which are called with the same argument. So this power distribution is more clear on the lower graphs. So we have like most of the functions being called with the same arguments. And so, I mean, given that we observe this in the wild and also in the benchmarks, one thing that we can do is to optimize the functions to the values of the arguments. So, for instance, here I have an artificial benchmark, and if I know that n is going to be 59, for instance, I can generate a much better code for this function. I can, for instance, eliminate the test on the top here, like the type test. I can replace the reference to n by its value, its true value. Oh, I already know the result of this conditional test here, so I can cut it off too. So we have a much more clean version of the function. So that's what we are trying to do. I will be showing performance numbers for benchmarks. I mean, it's hard to get performance numbers for the web pages because they run for a very short time and there is a lot of I/O going on. So generally we use benchmarks. I mean, in the literature we use benchmarks. And they're a little bit different in the sense of that they manipulate different types. Like the web pages, in general, they manipulate objects and strings. And the benchmarks, they are more integer intensive. So when I analyze the types of the arguments which are passed to the functions, I will see that the benchmarks, they're more likely to receive integers, for instance. So there are some differences here between the benchmarks and the web page. One of the discussions that we have with the reviewers in the rebuttal and also with our Shepard was if the benchmarks were meaningful enough. So yes, they are a little bit different. On the other hand, our optimizations, they translate to object and strings too. And in both cases, we saw this this power distribution in the number of function calls. So we can do a lot of things with integers. So we're likely to do well with the benchmarks. With the web pages, we can do a lot of inlining of closures. We can replace object properties like a.length by its value. We can resolve tests like this, which use objects. So we'll talk about the code specialization that we do here. So we are working with a just-in-time compiler. So we are compiling the code while we are executing it. We can do this in many ways. Like we can compile a function immediately when we see it, like V8 does. Or we can interpret the function and then compile it while it's being interpreted. That's what we will be doing. So that's what IronMonkey plus SpiderMonkey do. And the big advantage of doing code generation is that, for instance, we have runtime information, and we have been talking about this on Monday mostly, right? And so we will be capitalizing on this runtime information. We'll be capitalizing on these values of the arguments passed to the functions. So speculation is a trick that just-in-time compilers do a lot. It's sort of a reckless game, it's a gamble. I mean, it may be good, it may be bad, depending if you speculate wrongly. So, for instance, you can assume that the type of a variable is an integer, but then if you have an integer overflow, we have to fall back into a larger type. We can assume that the properties of an object are fixed, and then we can derive a class for that object. But if the user adds or removes something from the object, then we have to recompile. We can assume that the target of a call is always the same, that closure will be always the same. But then if it changes, we may have to recompile our code. So we assume that something will hold, and if things changes, we will have to pay for that. In our case, we are assuming that the arguments of a function will be always the same. If they change, we will pay for that. So I will show how we optimize this example here. This is a similarity search, and it's a very simple similarity search. I have a vector, V, it has n elements. I'm looking for an element from V that's the closest of Q. So it's a linear search, it's very simple. So the question is, what can we do once we know V, Q, and N? How can we optimize this code? So that's what we do. Here I have the control flow graph of my function. It's a little bit weird. It has two entry points. I mean, just-in-time compilers generally will have this. Here is the ordinary entry point in case I'm entering the function from its beginning, like I should do. And here is in case I compiled this function while it was being interpreted. So I will fall in the middle of the code. So I have two entries. The first thing that we can do is to replace these references to the parameters by their values. How do we discover these values? We look into the stack of the interpreter. So we just go there and ask the interpreter what's the value of all the arguments of the function, and we do this replacement. It's the first optimization. One thing that we can do here, not showing, is that we could inline closures, like JavaScript can receive functions as arguments, so we can just inline them right away if they're small enough. Actually, we are inlining everything, we use no heuristics, but we could use some heuristics too. We can do some dead code elimination. We had some discussion if that was the right name, maybe it's dead code avoidance. Given that we hope that function will not call again, I mean, we don't have to generate all this code here. Like, we're assuming that we're entering the function through this on-state replacement block. So, I mean, we just avoid all the overheads of producing this code here. So, instead of having this function here, we end up with this one here, which is a little bit shorter. We can do some array bounds checking elimination. In JavaScript, ABC, it was surprisingly difficult because our alias analysis was not good. So we eventually had to settle for a very simple approach. We try to find patterns like this. I initialize a variable, I test against bounds, and then I increment the variable. And then if this variable is used as an array access, I check and the limits of the array. And if they match, I can do the elimination. I mean, I can remove this code here. In JavaScript, all the array access, they are guarded because it's a type-safe language, so I can try to eliminate some of the guards. And we end up being able to eliminate arrays in most of the induction variables. So I end up from this code getting something like this. I can do loop inversion. That's a classic textbook optimization. You may ask what this has to do with our work. Well, it has something to do. Loop inversion is the thing of changing a while loop into a repeat loop, so that I can replace an if and I go to by just an if in the end here. In our case, we can, in general, we have to surround the repeat with a conditional because the loop may iterate like 0 times. So in our case, in general, we can solve this test here because we, in general, know the bounds of the loops. So we just will not generate this little code here. Yeah, it's a small thing, but I found it neat. So we can do this kind of optimization too. And we can do constant propagation plus that code elimination. So that's the optimization, the combination that gives us the largest payoffs. So I can replace all the uses of a value by, by the value itself. And at this point here, we would do some inlining too. I mean, every time you have some function that has been called, like even some method object properties, we could inline them right away. And then we use like ZADX, sparse constant propagation. So in general, we can eliminate some conditional tests too. Like sometimes you can solve at code generation time a conditional, so just cut it off and you don't have to produce code for that. So this optimization, this combination can streamline the code quite a lot. And so, I mean, in the end, for this example, I end up from this code here getting something that's like this, much shorter, much smaller. One of the benefits that we have observed is a substantial code size reduction. What would be very useful to us, as I will show on the experiments. So, as I said, we have implemented everything here in IOMonkey. I mean, we got a lot of help from the people from the Mozilla. I mean, if you want to do research with them, it's really cool. I mean, they're supportive. So, we have this code running now. It's publicly available, it's online. The tests are with this hardware here. I will show numbers for these 3 benchmarks. They are like used in the Mozilla Foundation. They are used in other JavaScript papers too. And we also got some benchmarks from Richards et al. They are from Purdue, so they have this tool that extracts JavaScript benchmarks from web pages. So we can, it's hard to show runtime numbers for the web page, but we can at least show code size reduction, which is cool. So here I have a set of optimizations. Parameter specialization is just this thing of replacing the parameters by their values. And also we do inlining, like we have a closure, we inline it right away. Constant propagation is, classic constant propagation. Loop inversion, I just showed before. That code elimination and bound check elimination are optimizations that remove a little bit of the code. As you can see here, I'm giving the percentage of speed up that we got with our optimization. So we could speed up, for instance, Sun Spider by over 5%, and V8, which is a larger, the benchmarks here larger, we could speed up them by 4.83%. So yeah, the speed up seems to be very consistent across the benchmarks. Compilation overheads, we may increase compilation overheads, but surprisingly sometimes we reduce it because the code becomes so short that the register allocator just doesn't have a lot of work to do. So sometimes we can reduce compilation overhead. So in blue, we are increasing compilation overhead. Sometimes we increase the compilation overhead a lot, like here. Most of the time we'll be increasing compilation overhead. We are applying 5 optimizations. But sometimes we decrease it, like we got some reductions, like in 7% of the compilation overhead. Code size reduction, we observed like the code that we produce is much shorter than the code that the baseline IAMANC compiler would produce. Here I'm comparing the same function. Here may be compiled many times. That's how a just-in-time compiler works. And you may recompile the function many times because some speculation went wrong or just discover some profiling information, and then it recompiles the function. I'm taking the shortest size of each function. So on the average, like for these benchmarks, we got this reduction, like from 15 to 19% of code size reduction. For the web pages, we got like these reductions here. These are like artificial scripts that we extract from the web page. It's not really the true web page. We're just downloading some script. In Yahoo, we got 42% of reduction, but we just compile 3 functions, so it doesn't say much. Sometimes we have to de-optimize the function because the function was called again with different arguments. We had to de-optimize functions pretty often. Like here I have the number of functions that we compiled for each benchmark. Here the number of functions that we could specialize. We don't specialize every function. We specialize functions that are compiled if they're called from the interpreter. And here the functions that we have to de-optimize because they were eventually called again with different arguments, so we had to de-optimize them. We increased the number of recompilations a little bit, but not too much. IAMANC recompiles functions a lot already. Because it does type inference, sometimes the type changes. It compiles the function after 10,000 iterations of some loop where the function is called 10,000 times. Or if the loop iterates 40,000 times, it recompiles again with a better, doing some more aggressive optimizations. So there is a lot of recompilation going on already. In our case, we increase recompilations by this factor here, less than 10% on the average. Because we had to recompile every time the function was called again with different arguments. So that's it. I think this paper has advanced the state of the art in terms of speculation for just-in-time compilers. All the code plus some more explanation about our techniques, it's available on this repository. We are still working on this. We're doing some looping rolling right now and overflow check elimination because JavaScript represents the numbers as floats, but the compiler generally can represent them as integers. So there's a lot of overflow checks there, so we're working to eliminate them. So, and thank you.
Thanks, speaker. Are there questions? So I was going to ask, did you measure the cost of the de-optimization? So in some cases you benefit, but in other cases, because you've done this extra work, you actually lose. Did you actually measure that?
Well, what do we mean? We measure the compilation overhead. So our compilation overhead includes the many times, the extra times that I had to recompile a function.
I see. So you actually, so even in a case where you actually made a mistake by specializing, in other words, the next time you executed it, you have to actually recompile it entirely. Even with all those mistakes you made, you still end up with a decrease of compilation time of 10% or something like 7%.
Yeah,
is that right? Wow, that's surprising.
But there's one thing here. Generally, when we compile these functions, it had been there's some loop that has iterated for I think 10,000 times at least. When SpiderMonkey, which the interpreter calls the just-in-time compiler. So the function is likely to be very hot. It's likely to run more.
I see. So you really don't. Okay. So you don't get invoked until you have a hot function.
Oh, yes.
And the assumption is that, that in that hot function, you may only enter that once in the whole execution of the program.
Yes, that's the bet.
Okay, yeah. Do you see this being a benefit from short-running programs or longer-running programs in terms of many JavaScript JavaScript websites just execute very briefly and then stops?
Well, we try to measure performance numbers for the web pages, but we could extract the scripts using a tool from Purdue. But the runtime was so short that the time would fluctuate too much, so we will not really trust the numbers. We didn't know if we were getting good performance numbers. So if the benchmarks, they run for a longer time, so it's much easier to measure numbers. So if the function runs for a longer time, it's likely to benefit more from our optimizations.
That's good.
Hi. Hi, I'm Robert Malik, Qualcomm Research, Silicon Valley. So we are actually working on pretty similar stuff. First, we are looking at types of arguments instead of values. And you are actually doing it like specialization, partial specialization based on values, right? And I was wondering the type of guards that you're generating for your specialized version. What kind of guards are you putting there? For example, for functions, if you're passing a function pointer, then check that is needed for making sure this function pointer hasn't changed. It sounds a little bit complicated. The other thing is that like 60% of the time you're fine with this specialized version, whereas the other 40% of the time, there are cases like the V8 benchmarks, even the type of arguments are going to change, and they're alternating between, say, object and integer maybe. And in those cases, I feel like performance is not going to be good because you're specializing and it's going back to the general version. You have to de-optimize and then have to specialize again, and it's going to be like a circle of doom because performance is going to significantly be degraded. I was wondering if you have problems like that, and you address those. Sorry, there are two questions.
Okay, maybe I should answer the first one.
Yeah.
I didn't tell the whole thing, but there's a lot of heuristics here. We just specialize a function once. So if we specialize the function and it was de-optimized, we will never specialize it again. And that's just to avoid having to specialize a function that's going to be called many times. And
that makes sense. I mean, do you have like stats about what percentage of functions acted that way, or?
Well, I have this one, chart here that says that for these benchmarks, we had to de-optimize these functions here out of this total. Yeah, around like 60%. But if we de-optimize a function, that's it. You don't touch it again. And we have a lot of guards, but most of the guards are inserted by the original baseline compiler because it does type specialization too, and promotes objects to integers. So we have guards like against overflows, for instance. Our technique only inserts one kind of guard. Every time we check a function, I have a hash table to see if it's being called with the same arguments. So just verify if the arguments have changed. And then if they haven't changed, we use the specialized code, otherwise we have to de-optimize.
Okay. Yeah, but complexity of those guards, like for function, was not bigger than integers, right? I mean, it was...
Oh no, it's much smaller because you have many functional, you have much more integer arithmetics than function calls. You will have to check these guards before calls.
Okay, thanks a lot.
I think we better move on. So let's thank the speaker again. Our next speaker is Jacques Pinard from Purdue University. Jacques is a student.